Good afternoon, everybody. Welcome to this session on the Mini Moon seminar series. And the speaker is Mr. Kenyo Wu, and in Chinese would be Yu Xianyang. I don't know whether he knows that his name pronounced in Chinese Wu Yu Xianyang. In fact, if you read his CV, Mr. Wu, he said that he's learning Chinese, or he can speak Chinese. We'll test him later on. And he's a very interesting person in the sense that because when I invited him, he wrote back. He said he hesitated because I wrote to him calling him Professor Wu, and he said, "Oh no, I'm not a doctor. I'm still a graduate student." And then when I talked to him just now, and turns out he just started his graduate study. so he said that he hoped to graduate in 2025. So still 2 years late. So that means he's just starting his graduate study. But on the other hand, if you look at him, because I found him because a very interesting paper he published in the Earth and Planetary Science. Earth, Planets, and Space Journal, and called the effects of magma generation and migration on the expansion and contraction history of the top, which must be the topic of his talk today. But then I want to just spend a couple minutes here because his CV is very interesting. He got his finished his undergraduate in Kobe University, and then he went to Tokyo University to get his master's degree, and switching to the moon, to the lunar science. And now he's there. Here he is continuing his study on the moon at the same university, Tokyo University. And he during his previous study already, he went to a lot of meetings presenting his results in Japanese conferences and workshops. But I received a number of awards for young students, undergrad and graduate students. But very interesting is that you have to confirm this. He said he is qualified. He got a certificate or license to teach in junior high, right? You're ready to teach in junior high, and you also get a license to qualify you to teach in high school. It's a senior high school. And then he also got a certificate called last year, which is called the University of Tokyo Future Faculty Program. So you're ready to go back to Tokyo University, right? To be a professor. That's very, very ambitious. Very good. Okay, Kenyo, start your talk now. Right, please.
Hello everyone, my name is Kenyo Yu Shenyan, a graduate student at the University of Tokyo, and I would like to talk. Thank you all for inviting me to this wonderful seminar. My research focused on the summer history of the lunar interior, and I'm grateful for the opportunity to share my work with you today. The topic of my talk is evolution of the lunar interior caused by migrating magma in the two-dimensional annular mantle, and I'm excited to discuss it with you. Modeling lunar evolution that is consistent with the observation is necessary for understanding the long-term dynamics and unraveling the formation and evolution of the moon. Observation of radial change and volcanic history constrain the dynamics and lunar interior. There are several observations in the summer history of the lunar interior that are difficult to explain using previous models. These include early expansion, later contraction, and long-term Mare volcanism that peak at 4 to 3.5 billion years ago. We further show the detail of these observations in the next slide. Some previous observation has revealed that the moon has undergone a period of expansion in the early history. NASA's Gravity Recovery and Interior Laboratory GRAIL mission in 2011 measured the distribution of lunar gravity. This mission shows globally linear gravity anomalies like this. These are known to be dikes formed by magma intrusion, and the feature suggests an increase in the temperature of the lunar interior that caused the early expansion of the moon for a few kilometers by 3.8 billion years ago. In addition to expansion in the early history, the previous observation has revealed that the moon has undergone a period of contraction in the later history. The Lunar Reconnaissance Orbiter Camera in 2009 takes a high-resolution photograph of the lunar surface. The orbiter camera shows lobate scarps on the global moon, like this. These scarps, which mean the source faults, are formed in the compressional field, suggesting a decrease in the temperature of the lunar interior in the later history. The study showed the moon had contracted by about 1 kilometer in the last billion years. It is a long-standing issue to reproduce the radial change in numerical models. In the classical model of thermal history, where thermal conduction and internal heating are considered, the initial temperature in the deep mantle is assumed to be low as around 1000 Kelvin. This is the surface, and this is the core mantle boundary, and deep mantle temperature is 900 Kelvin. In this case, radial expansion by thermal expansion occurs because the internal heating in the deep mantle. Then radial contraction occurs owing to the cooling from the surface boundary. So the model shows the early expansion and later contraction, shown in this figure. The important point of the model is that the deep mantle in the initial state must have been lower than 100 Kelvin, 200 Kelvin, 200 Kelvin more order for the moon to expand. I'm sorry, 200 Kelvin in the order for moon to expand. It is too low to be consistent with the initial condition after giant impact and mantle overturn hypothesis. This hypothesis suggests the initial temperature in the deep mantle is as high as 900 Kelvin. Besides, the studies of volcanic activity on the moon revealed that the Mare volcanism was inactive before 4 billion years ago, become active between 3 and 4, with a peak at around 3.7, then mildly continued until 2 billion years ago. To account the early activation of volcanism, previous models suggest the upwelling of overturned layer enriched in ilmenite-bearing cumulate, IBC, by convection. After the magma ocean, the residual layer, the red or yellow layer, which is dense and enriched in incompatible elements, is slow to have overturned and sunk into the deep mantle, like this figure shown. The previous mantle convection model suggests that overturned basal magma, rise as a mantle proof owing to internal heating by incompatible heat producing element. And the timing of the ascending hot plumes is around 3.7 billion years ago, consistent with the observation like this. However, the laboratory and numerical experiments suggest that upwelling of the lunar ice layer by thermal boundaries alone is difficult. The lunar ice layer is compositionally too dense and too thin, like this. So this is the buoyancy number, and this is the layer depth ratio. And when we put the IBC, but the value of IBC layer, like this yellow circle, it's too dense and too thin to cause the form hot upwelling pool. That's called the Mare volcanism. In this case, the overturned layer like this become a stable layer in the deep mantle. It is also difficult to construct a model that account for the early increase in volcanic activity, but also for the longevity of volcanism. Some three-dimensional spherical model consider the effect of internal heating, conduction, and convection on the thermal history of the lunar interior. This model assumes the presence of region is enriched in heat-producing elements known as frozen creep terrain (PKT) on the near side of the Moon. The model shows that the partially molten region generated by radiogenic heating could have been present in this white region, the partially molten region, that could be present on the surface for more than 3 billion years. But while this model successfully explains the radial expansion of the near side, it does not account for global expansion, including the far side, the green line, the radial change diagram. Besides, the model does not account for the early increase of volcanic activity. It's the age and this melt production rate. So this model did not account, does not account for the increase of the early volcanic activity. To summarize, we'd like to produce the global expansion in the lunar early history when the initial temperature in the deep mantle is high as 900 Kelvin, and the early history of Mare volcanism, and long-term volcanic history that continues for a few billion years. To query the physical processes through which the features arose in the history of the Moon, we decided to add some these effects to the model. First, as for radial expansion, previous study takes only thermal expansion in account. We further considered the effect of volume change by melting of the mantle, as shown this term. This is a radial change, and this is the temperature, the differences of temperature by the thermal expansion. And this is the melt content, the volume of melt by melting of the mantle and melt content. Then, as for the volcanism, previous studies does not consider the effect of magma generation and migration. Magma ascent is treated as the permeable flow and incorporated into the equation as a relative velocity between magma and matrix. So we will first present a one-dimensional spherically symmetric model to show how melting affects planetary expansion and contraction history. Here is a one-dimensional spherically symmetric model submitted EPS as planetary and space. Here is the one-dimensional spherical symmetric modeling. This is a diagram of amount of magma showing the melt distribution of the edge and radius. If the initial temperature in the deep mantle is high enough to be consistent with the giant impact and mantle overturn hypothesis, magma is generated in the deep mantle and ascend to around 1400 kilometers. Then decrease. The partial molten region shrinks with time. The radius change diagrams show the expansion contribution for melting. The right blue line is important, and that's the total radius change, the purple line, which is the sum of these two effects. Is consistent with observed expansion and contraction. However, there are still some issues with this model. Firstly, it does not consider the effect of mantle convection. Secondly, the one-dimensional model shows how far the magma ascends, but it is difficult to relate these results with volcanic activity. So, in this study, we developed the two-dimensional polar rectangle model of the lunar mantle evolution, where convection and magmatism transport heat, incompatible heat-producing element, radiogenetic element, and basaltic component, which includes the IBC component. The momentum equation for mantle convection is written in the term of pressure, buoyancy, and viscosity. And the differences between the velocity of magma, the small u, and that of matrix, large u, is proportional to density difference and permeability k between them. In this two-dimensional model, the initial condition is estimated for the mantle overturn model. We assumed it here that the deep mantle is occupied by the compositionally dense IBC materials, and it's a surface in the core mantle boundary. So the deep mantle is occupied by compositionally dense IBC material, enriched in heat-producing element at the heating rate by the heat-producing element. And the initial temperature in the deep mantle is as high as 1900 Kelvin. Here's the animation of our model. The four frames you see the temperature and melt content. So 0.2 mean 20% melted, and heating rate from internal heating by heat producing element, and bulk composition. In bulk composition, the blue present areas enriched in IBC component, the heavy component, and while the red represent area is more olivine-rich material. So I will show you the animation. But first, I'm sorry. First, magma is generated in the deep mantle because we assume the deep mantle is enriched in heat-producing element. And finger-like structure or melt fingers develop on the top of the partially molten region in the deep mantle and at the depths. Then, following the development of melt fingers, partially molten plumes like this then rise to the uppermost mantle along some melt fingers. The plume transport the heat producing element and IBC component to the uppermost mantle. Then the plume solidified upon the cooling from the surface boundary. Like this, the partial molten region cooled and solidified gradually. I will share you it again. So here, the magma is generated in deep mantle and then migrate uppermost mantle. Then this activity continues for a few hundred, few billion years ago. But as the activity declined with time, the partial molten region shrink and cooled. Okay. So the radial change for such two-dimensional annular model is consistent with observation. The radial change in the left panel is two-dimensional. In two-dimensional, the radial change in the left panel shows that the lunar expansion and could not account for the thermal expansion alone, which means green line, but it can be explained by adding the contribution of melting, it means light blue, and the total radius change, the purple, which is sum of the two, reproduce very well the initial expansion and later contraction. Compare these results of the one-dimensional model. The one-dimensional model expands once and then contracts gently, whereas the two-dimensional radial variation, a chart is bumpy. This and the scale is also larger than 2D. Oh, I'm sorry. This also larger than 2D. This is because the magma ascends the plume-like manner in the two-dimensional model, whereas the one-dimensional model does not take into account the effect of mantle plume. The expansion in the one-dimensional model corresponds to the initial expansion in two-dimensional model, like this. It corresponds. We believe that this difference is caused by spatial multidimensionality. Furthermore, the results of the two-dimensional model are more consistent with observed history of volcanic activity than those from the one-dimensional model. Even when melt fingers migrate upward and the planet expands like this, the partial molten region does not reach the uppermost mantle, so the melt fingering does not cause Mare volcanism. At the age in number two, the period when partially molten plumes rise the uppermost mantle, that is consistent with the peak period of volcanic activity of the moon shown here. And when the pulse of expansion here, the similar partial molten plumes ascend from the deep mantle. Then, the partial molten region is cooled and solidified gradually, but the plume magmatism continued for a few billion years, and this diagram shows the partially molten region still remains in the uppermost mantle. The partially molten plumes transport the IBC component, like a blue area, and heat-producing element, like yellow and red area, like this. So, both magma generation and migration are important for understanding the internal heating dynamics of the moon. Then, we studied how the duration of magmatism is controlled by internal heating. To understand the long history of magmatism, we calculated the case where the mantle composition is uniform. The snapshot of the model shows the partially molten plumes migrate upward and reach the uppermost mantle, like this, the white counter in this figure. However, this activity does not continue, and partially molten region by the plumes is cooled and solidified quickly. This is because the migrating magma extracts the substantial amount of heat-producing element from the deep mantle within a few hundred million years. Magma is not generated in the deep mantle, in the depleted mantle. However, in the case of model, in the reference case, where the differentiation of mantle materials by magmatism is considered, some materials enriched in heat-producing element and IBC sinks or remain in the deep mantle, owing to the compositionally in this negative buoyancy. I mean, and this white counter is main red content, so it's magma generating and migrate upward. But we will focus this region. This region is become cool and solidified, and a lot of heat-producing elements remained in the mantle, and it has also IBC component. It's a heavy component, remain in the mantle and dense in the deep mantle, sink in the deep mantle. So the plume magmatism continued through the 44 billion years ago. I will show this animation again, and solidify and remain in the heat-producing element. And this heat-producing element causes another magma generation and migrate upward. So, we conclude that the compositional density is important for long-term magmatism. Next, we focus on the two modes of magma transport, a melt fingered and partially molten plume. The reference case shows the melt finger developed, then partial molten proves rise. To understand the property of magmatism and how the Mare volcanism occurs, we delineate the velocity of the matrix around the nascent finger. The figure for around 400 million years shows the melt finger developed and grew upward owing to matrix expansion around the fingertip caused by injection of upward migrating magma over the partially molten region. After 100 million later, the development of melt fingers, partially molten plumes grow owing to buoyancy of magma. The stem of the melt finger, indicated by yellow dust circle, so in figure like this region, these areas, the area becomes thicker than fingertip with time. In the thickened area, the yellow dash area, the matrix migrates upward. This figure shows that the melt fingers are important for the first step of magma migration, and the partially molten plumes strongly ascend the partially molten region to the uppermost mantle to cause the volcanism that accounts for Mare volcanism. To understand the dynamics, what the condition melt fingers and partial molten plumes occur, we calculate more models with different parameter values. Firstly, we fix the mantle viscosity and change the permeability, which is determine the ascent or velocity of magma. The permeability, as permeability is determined the ascent or velocity of magma. In the case with low permeability, this is a reference case, the GIF movie of reference case, and this is a case which the permeability changed and low permeability. We assume the low permeability model. In the case with low permeability, the partial molten region forms the large plumes, resulting in the larger planetary expansion than a reference case. It's a larger change at this age. However, this larger expansion is much larger. Yeah, of course, much larger than observed expansion, and the peak expansion occur greater than that of the moon. In the model that consistently explains larger expansion, the velocity of the magma relative to the matrix is typically about 2 centimeters per year. Secondly, we fix the value of permeability and change the mantle viscosity. The diagram of radial change, right diagram, illustrates that the amplitude and peak of the expansion are not related to the mantle viscosity. However, the model with low mantle velocity, this is low mantle velocity, makes mantle convection active in more consistent with the observed history of Mare volcanism. I'm sorry, this is it's the high mantle viscosity and it's a low, which means the reference case. So you will see the high viscosity, the Melt fingers migrate upward, but then gradually shrink with time. The secondary migration is not occurred, but the reference case, the partially molten pools, uh, migrate, and partially molten pools rise, and this activity continues for a few billion years. So the favorable value of mantle viscosity is lower than assumed some previous mantle convection, and it's comparable to that in Mars. So here, we value some initial parameters to see how they affect radial change. First, we value the initial temperature in the deep mantle within this range. So the result shows the diagram of radial change shows that in what temperature the 1400 kelvins, in the 1400 Kelvin, the expansion is slower than the peak compared with the reference case. And so in the reference case, I plot in the black dash line. We also value the initial condition for the concentration of heat-producing elements in the crust and mantle, and change as a parameter for the average concentration of heat-producing elements in the lunar mantle. We found that the expansion occurs when the concentration of heat-producing elements in the crust is 4 times that in the whole mantle, which means the whole mantle is more enriched in heat-producing elements than the reference case, the red curve. And maybe also the light blue curve, which means the mantle is more enriched the 16 times than the crust. I'm sorry, I inversed. The crust is more enriched in the that in the mantle, more 16 times. It can account for the early expansion, but no expansion occurred when the ratio is 32 times the blue line. On the other hand, okay, the detail of distribution of heat-producing elements is that initial mantle does not affect of expansion and contraction history much as in showing figure. Maybe so the line, the 1 per 1.5, which means that we assume the more uniform in the the heat producing element is more uniform than this reference case, and 1 per 5.5, the brown line is the profile of the heat producing element is like this. So yeah, maybe it's not affect expansion and contraction history much, but when we assume the deep mantle is more enriched in heat producing element, the expansion is earlier. It's small changed, but not much changed. And this result is consistent with previous suggestion that the overturned material remained in the deep and shallow mantle and did not sink in the deep mantle. So, I'm sure the conclusion. Uh, in my work, to understand the mantle dynamics in the moon, we developed the two-dimensional annular model. In the future, we have a plan to develop the three-dimensional spherical model. But now, the step by step in this study, we focus on the two-dimensional. So we considered a mantle of convection and enter the grateful grateful effect of magma system. I'm sorry, which means migrating magma transport the heat incompatible heat producing element and basaltic component. The result shows the magma generating in the deep mantle and finger-like structure, melt finger develops in the deep mantle. And then partially molten plume rise and ascend uppermost mantle, then solidify with time. The partially molten plume transport I'm sorry, the heat producing element and IBC component, which means the basaltic component, and remain the uppermost mantle. So our model shows that the magma generation, migration, and ascending partial molten plume in the mantle account for the history of radial expansion and contraction and Mare volcanism of the moon. And that's my end of my presentation. Thank you very much.
Yeah, thank you very much for the presentation. And then by the way, I think you have already said it that the HPE in your slides means heat producing elements, right? Am I correct? And for the heat producing elements, are they the radioactive elements or other things you have in mind?
Mm-hmm.
What kind of heat producing elements you're referring to?
Oh, I'm sorry, that question for me.
Yeah.
So
I'm asking you actually.
so the meaning of what you said is how what previous model assumed the heat producing element, like the distribution or whatnot, right? I'm sorry, I can't hear your question. I can't talk quickly.
And also that in your model, there seem to be a symmetrical. That means you know everywhere you have this approach now. But
Yes.
however, for the moon now we only see this on one side. We have this near the Imbrian mare.
Yes.
Yes. I would say more more heat producing element region, but not other places. So it's asymmetrical. So what's the reason for the asymmetrical distribution?
It's tough questions for me in two-dimensional model. So in our model shows the magma migration since the IBC layers migrate upwards, the uppermost mantle, and heat producing elements are here. Maybe it's also seen the porcelain PK like PKT, but in this model we can't account for the asymmetry of the moon very, very well. Which means maybe the initial distribution of uh, the the overturned layer is
the crustal thickness, would that matter?
Yeah. Maybe the result will be changed.
Yeah.
Maybe.
All right. Question from the audience. Please raise your hand or just write down your question, in the chat box. If you
or
you
comment.
just turn on your mic, and you could ask questions. I see some experts here.
Hello?
Yeah, Lin Qihong, yeah, you have a question? Your questions? Yes, please.
Okay. Yeah, so
Thank you.
good afternoon, Professor. So I have one question is because your research is the topic is about this heat model of the Earth, of the Moon. Sorry. Yeah. So I have one question is because we know the Io, I think it's called Io. Yeah. So this is one of the satellite of the Jupiter. They have very active the volcano because they're close to Jupiter, so tidal force can
tidal heating.
Heat source. Yeah, tidal heating. So my question is because we know in theory the moon was very close to Earth. So moon was a very short orbit cycle. So in theory, when the moon they are close to Earth, they also have a very clear that tidal heating. But follow the time, moon are getting far and far to the Earth. So will this kind of energy input decrease to interference to your model's resource? Because since that your model didn't have consider about this tidal heating effect. So this is my question. Thank you.
So is the meaning of what you said, I consider the tidal heating or not? Or if I consider the tidal heating, what will happen in the model, right?
Yeah, because indeed tidal heating also causes a more complex resource. The tidal force that causes the crack in the rock, but crack they will be decrease the heat coefficient.
Yeah, differently. In the model, we can't we can't enter the effect of tidal heating because it's so strongly dependent of the assumption. So the previous model didn't account for the effect of didn't enter the effect of the tidal heating as a case of moon, and some researchers the research about the electrical conductivity of the moon shows the tidal heating of the moon has a small effect on the thermal history of the moon. So maybe we don't have to take into account the effect in the lunar interior model. I hope.
Okay, good. Because this is a prone generating process, is it caused by instability or thermal instability? Or something?
Yeah.
And does it have anything to do with the rotation period of the moon?
Yeah, the rotation, the period of the moon.
Because it gives you some kind of like a centrifugal force, right?
Yeah, right.
Respect to the gravity, and that as Qihong was mentioning at the beginning of the Earth-Moon system, the moon was much closer to the Earth than now, so that it had been rotating also much faster than
previous moon, the faster.
So, but in your calculation, you have not put into the centrifugal force anyway.
Yeah.
So the whole system is a stationary. Any other questions? Any other questions from the audience? I think it's a good opportunity, to ask a young lunar scientist and who want to be a teacher in a high school and also at the university at the same time. Okay, now in your slide you have this slide you have you're showing you have the ilmenite bearing cumulates, IBC.
Yes.
Can you explain that a little bit, because to some of us who are not familiar with lunar science, what's the definition? What's the mechanism for forming the ilmenite bearing cumulates?
But the formations.
Yeah, the IBC. IBC
formation. you talking about the how the IBC formed.
Right.
What?
Right.
Yeah, right.
It seems to be a very important element, a factor in your model.
Yeah, yeah. The previous overtime model has an Parmentier 1995 maybe, or the residual layer in the after the magma ocean that has a high density component and incompatible element sank in the deep mantle, and we assume this the parameters, and which means the IBC layer is 7.5 times enriched in heat producing element. So we consider the effect and relatively to distribute the profile. Yes. So is that answer for your question or not?
Yeah, fine. I mean, if we don't, it's not very clear, then we could always go back, to look at the books, or
Thank you. Thank you.
Any other questions from audience?
I'm I'm sorry to speak the Chinese immediately.
No, next time you have to give the talk in Chinese.
I hope.
Yeah.
But
right. Okay, good. If no further questions, no other questions, let's end the session, which is a very interesting talk. I think that if later on, for some of us who have read a little bit about lunar science, we will think that that is a very interesting calculation, a model calculation being done by Kenyo-san. And remember that he's just a starting graduate school, PhD student, and he's doing a very good job. And okay, thank you so much.
Thank you very much.
And we hope to see you. Will you come to Taiwan to visit us?
Yes.
Very good.
I hope.
Let's know. Right, we welcome you to visit us.
Thank you.
Yeah.
Thank you.
Okay, good. Thank you.
I will contact.
Have a good evening.
Maybe.
Yeah.
Thank you very much.
Yeah. Bye-bye.